Picture this. You're training a little robot to find a charging station in a building. You don't hand it a floor plan. You don't tell it where to go. You only give it feedback, a small positive signal when it gets closer, and a negative signal when it crashes into something. At first, it looks hopeless. Random bumps, random turns. But after enough tries, it starts moving with purpose. It takes corners smoothly. It avoids dead ends. It behaves like it understands the building. What's actually happening is less magical and more structured. We're describing the world as a particular kind of decision problem. That structure is called a Markov decision process, or MDP, and it's the foundation underneath a huge chunk of reinforcement learning. Today, we'll build MDPs from the ground up, talk about transition dynamics and reward functions, and then push into the real world where you can't even fully see what's going on. POMDPs. Reinforcement learning is about an agent learning to make decisions by interacting with an environment. It tries things, it gets feedback, and over time it learns behavior that maximizes reward, not just right now, but over the long run. MDPs are the clean mathematical wrapper around that interaction. They give us a common language to describe tasks like games, robotics, inventory control, and recommendation systems. And once you have that language, you can start asking precise questions like, what does optimal mean here? What information does the agent need? How do randomness and delayed consequences change the problem? Here's the roadmap. First, we'll define an MDP and really focus on the assumptions that make it work. Then we'll open the hood and examine how transitions and rewards shape learning. Finally, we'll confront the messy reality that agents often don't observe the true state, and that's where POMDPs come in. Let's start with the big idea. An MDP is a model of a world where decisions happen in steps. At each step, the agent is in a state. Think of that as a snapshot of what the world looks like right now. The agent chooses an action. Then the environment responds. It moves to a new state and gives the agent a reward. That's one interaction. Then we do the next step, and the next, and the next. If you've seen the formal definition, it often comes as a bundle of symbols, states, actions, transition probabilities, rewards, and a discount factor. But what matters most isn't memorizing the bundle. What matters is understanding the assumptions those symbols are enforcing. The defining assumption is the Markov property. It sounds technical, but the intuition is simple. If you know the current state, you have everything you need to predict what might happen next, given an action. In other words, the future doesn't need the entire history. It doesn't matter how you arrived here. What matters is where you are now. Here's why this is such a big deal. In reinforcement learning, an agent is constantly trying to connect cause and effect. If the state contains the relevant information, then learning is tractable. The agent can generalize from repeated experiences in the same state. But if the state leaves something out, like hidden velocity, or a timer, or a key you picked up earlier, then two situations might look identical to the agent, even though the future behaves differently. The environment becomes confusing, and learning can become unstable. So when people say the environment is an MDP, there's a quiet extra sentence. With respect to the state representation we've chosen. That's a subtle point that shows up everywhere. In robotics, the raw camera image might not perfectly encode everything needed, especially if something is out of view. In finance, the current price alone probably isn't a Markov state. In games, the screen might be enough, or you might need additional memory of what happened earlier. A second assumption is that decision-making is often modeled in discrete time. You take an action, then the world responds, step by step. Even in continuous systems like a drone flying through the air, we often sample time into small intervals, 20 milliseconds per control update, for example. It's a convenient approximation that makes the math manageable. Now, there's another ingredient that quietly shapes everything: how we measure success over time. Reinforcement learning typically cares about cumulative reward, not just immediate reward. This is crucial because many actions have delayed consequences. Studying for an exam doesn't give reward right away, but it changes future outcomes. Investing in maintenance doesn't feel good today, but it prevents failure later. To handle that, MDPs use the idea of a long-term return, often a sum of rewards, usually with a discount factor that makes near-term rewards count a bit more than far-term rewards. The discount factor also helps when tasks could run forever. It keeps the total from blowing up. So to recap the story, without drowning in symbols, an MDP is a step-by-step decision world where the current state plus your action is enough to describe what happens next, and where your goal is to maximize long-run reward. Before we move on, here's a quick mental example. Imagine a grid world. A little agent moves up, down, left, right. The state could be the agent's position on the grid. The actions are the moves. The reward could be +1 for reaching a goal, and maybe a small negative step cost to encourage speed. If the world is deterministic, moving right always moves right. If it's slippery, moving right usually moves right, but sometimes slides you up or down. That slippery version is still an MDP because the randomness is captured in the transition rule. Now we zoom in on the two parts of an MDP that truly define the environment: how the world changes, transition dynamics, and what the agent is trying to optimize, the reward function. Let's start with transitions. In real life, the same decision doesn't always produce the same outcome. You can press the brake pedal with the same force and still stop at slightly different distances depending on road conditions. A robot can apply the same motor command and drift because the floor is uneven. A trading agent can place the same order and get different fills because the market moves. MDPs capture that uncertainty with a simple idea. Instead of mapping to one next state, the world provides a distribution over possible next states. It's basically saying, given where you are and what you do, here's the range of things that could happen and how likely each is. This matters because it changes what it means to be smart. In a deterministic world, planning is like chess. If you see enough moves ahead, you can pick the best line. In a stochastic world, planning is like poker. You choose actions that do well on average and avoid strategies that collapse under bad luck. Now let's talk about rewards, because rewards are where the values of the task get encoded. A reward function turns an interaction into feedback. Sometimes reward is obvious. You win or lose. Sometimes reward is engineered. A small positive signal for progress, a small negative penalty for time, a big reward for reaching a target. A crucial concept here is that reward is not the same thing as the agent's objective in human terms. If you build a cleaning robot and reward it for picking up dirt, it might learn to dump dirt on the floor so it can pick it up again. If you reward a recommender system for clicks, it might learn to show sensational content that people click but later regret. This function is a specification. The agent will optimize what you measure. This is why people say, in reinforcement learning, you get what you reward. There are two common reward styles that really change the learning experience. One is sparse reward. You only get feedback at the end. +1 if you succeed, 0 if you fail. This is elegant because it matches the real goal, but it can be painfully slow to learn. Early on, the agent stumbles around randomly and almost never reaches success, so it has very little signal about what to do. The other is shaped reward. You add intermediate hints, small rewards for getting closer, penalties for wasting time, and so on. This speeds up learning dramatically, but it's also dangerous if your shaping accidentally changes what optimal means. If you reward getting close to the goal, the agent might learn to orbit near the goal without finishing, if finishing has risks or costs. So transitions tell the agent how the world reacts, and rewards tell the agent what to care about. Together, they define the entire learning landscape. Now, there's one more key piece that connects this to actual behavior: the agent strategy, called a policy. A policy is simply how the agent chooses actions based on what it knows. If the environment is uncertain, the policy might even choose actions probabilistically. In this state, take action A 80% of the time, action B 20% of the time. And the agent's goal is to find a policy that maximizes expected long-term reward under those transition dynamics. You can think of it like training for a sport. Your transition dynamics are the realities of your body and environment. Some days you're tired, some days you're sharp, and training has probabilistic effects. Your rewards are your goals: winning competitions, improving time, staying healthy. Good strategy isn't about one perfect move. It's about a policy that performs well across variability. That's exactly what RL is doing, just with math and data instead of pep talks. Everything we've said so far relies on one hidden convenience. The agent knows the state, but in many real settings, the agent never directly observes the true state of the world. It sees a camera frame, a noisy sensor reading, a limited dashboard, or a partial snapshot. That's not an MDP from the agent's perspective, because what it sees right now might not contain enough information to predict the future. This is the motivation for POMDPs, or partially observable Markov decision processes. In a POMDP, the world still has a true underlying state evolving over time, but instead of handing the agent the state, the environment provides an observation, something that depends on the state but doesn't fully reveal it. A classic example is a robot with sensors. The true state might include its exact location, orientation, and the positions of obstacles. The observation might be a noisy distance reading or a camera image where some obstacles are occluded. The robot doesn't know the state, it knows what it can currently sense. So what does the agent do? It builds an internal understanding over time. Instead of treating each observation in isolation, it combines them. What did I see a moment ago? What action did I take? What do I see now? That sequence contains information. It's like walking through a dark room with a flashlight. One snapshot isn't enough, but a stream of snapshots, plus your own movements, lets you infer the layout. This leads to one of the most important ideas in POMDPs, the belief state. A belief state is the agent's probability distribution over what the true state could be. It's like saying, given everything I have observed so far, here are the possibilities, and here's how likely each one is. If that sounds like filtering and estimation, that's because it is. POMDPs sit at the crossroads of reinforcement learning and probabilistic inference. This also explains why memory becomes so valuable in partially observable tasks. In an MDP, memory isn't necessary if the state is truly Markov. In a POMDP, memory is how you recover missing information. That's why modern RL agents often use recurrent networks or attention mechanisms. They create an internal summary of the past that acts like a learned belief. So the conceptual upgrade from MDP to POMDP is this. MDP assumes you can see the world's state directly. POMDP assumes you see only clues and you have to infer the hidden state while still making decisions. An MDP is the basic contract behind reinforcement learning. States, actions, rewards, and transition dynamics, plus the Markov assumption that the present state contains everything needed to predict the future. The environment's transition dynamics describe uncertainty and how actions reshape the world. The reward function defines what the agent is optimizing, for better or worse. And when the agent can't directly observe the state, we step into POMDPs, where learning is tightly tied to inference, memory, and belief about what's really happening. If you understand these three layers, you're holding the blueprint that most RL methods build on: value functions, cue learning, policy gradients, actor critic. All of it plugs into this framework. In the next video, we can take one concrete example, like a grid world or a simple robot navigation task, and derive the Bellman equations visually so you can see exactly why value is such a central concept.